Hey everybody, we're looking at force systems today. So we'll start with just kind of a quick run through, and then we'll look at a few of the examples from the worksheet and work those out. Um, Basically, a force system is a lot like the free body diagrams that we've been looking at, except a free body diagram. The word body just implies that there's one object, and if we're dealing with a system, then that means we have more than one object. So by definition, this is just more than one object. So pretty simple um, to think about, more than one object. A lot of times they could be stacked on top of each other. Sometimes they're side by side. Sometimes they're connected by a chain or a rope or a pulley or something like that. So you kind of have to analyze them. And if you think about each object in terms of the free body diagram on that individual object, that'll kind of go a long way. So, like I said, a lot of times you might have one object and something stacked on top of it. You might have objects that are side by side. You might have one object that's connected by a rope to another object. Um, these are also like elevator problems where you might have kind of a up and over like a pulley kind of system. So it's actually touching the pulley. There we go. That sort of thing. So all of those would be examples of force systems because if you look, there's more than one object in each of those little quick sketches. So that's just kind of what to expect and why these are different. You can kind of tell that some of these will be a little more complicated just because we're dealing with more than one thing. But like I said, if you stick to your guns and look at the free body diagrams, that'll help out a lot. So I thought we'd kind of jump in. You guys have probably started to look at the worksheet. There's 4 problems on here. I thought we would start on the back just because these are a couple of the easier ones, which seems like a better place to start. If you have a situation like number 3, where you have 2 boxes stacked on top of each other like this, the problem's asking us to find the normal force acting on each box. And of course, we know the normal force is a surface pushing back up on an object. And so if you look at the top box here, I'm just going to call that A and call this one B just so I can refer to them. Box A is just itself. And so box B is actually what's pushing up on box A. And if you think about this, it's like our diagram number 1 because it's horizontal. And so in that diagram, in diagram number 1, if you remember, the key relationship is FG equals FN. So if we can find FG, then we can find FN in this diagram. So pretty straightforward. We know it's 10 kilograms, so finding FG, we're just going to do 10.0 kilograms times 9.8. And we're going to get an FG of 98.36 there newtons, which means our normal force is also 98 newtons. So you can see right off the bat how your knowledge of the free body diagrams is going to help out a lot. So that's the first box. The second box down here, the tabletop's what's actually pushing up on it. And if you think about what's getting applied to the tabletop, box B has box A on top of it. And so both of these are going to kind of combine to give you a total FG in the downward direction, which means there's going to be a total FN, a normal force acting in the upward direction. So I think the easiest way is to just say, okay, well, the table's got to push up and kind of support both of these. So I'm just going to combine those masses. Basically apply the exact same thing, except when we go to find the FG, I'm going to go ahead and combine these. So I can just get a total mass of 30.0 kilograms. And I'm going to multiply that by the 9.8 so we can get FG. That comes out 294, and I know the normal force is exactly the same as that. So our answers there are these guys. If you don't like the idea here of combining, you could always come over here and solve them out individually and add them together. It's kind of whatever way makes the most sense to you, but that's all that one's asking for. So if you find a couple normal forces, that one's good. All right, let's hop down. Let's look at number 4. It gets a little bit more complicated. We've got some friction acting here. This one wants acceleration of the system. And so we've got a system because we've got 2 different boxes. We've got an applied force that's pushing on this smaller box. But if you notice, they're in contact. And because they're in contact, I think the easiest way to handle this one is to kind of pretend like they're one big object as well. And so what we're going to need, if we need acceleration, remember if we're looking at this as one object here, we've got an applied force acting this way. We're going to have friction acting this way. And then, of course, we've got Fg, and then we've got Fn pointing upwards. And so we're going to have to find frictional force before we can solve this out, because we need a net force. We've got an applied force. We've got that at 620, but we need FF. And so if you think about it in terms of FF, our equation, which is this, we need normal force. And so the way that we're going to get normal force, this is diagram number 1, because everything's horizontal, the force is being applied horizontal. So we're going to need to find Fg so that we can find Fn. So I'm just going to go ahead and plug in for that. So Fg equals ma. I'm going to treat these like they're one object. So kind of like what we did up top here for the second part, I'm just going to combine these masses. So we've got a total mass there of 185 kilograms. And we're going to multiply that by 9.8. So that we get Fg to come out as 1810 newtons. And because this is the horizontal first diagram, we know that normal force here is also 1810. So now we're kind of in business to solve frictional force. We have everything we need. So FF, we know normal force now. Coefficients given in the problem. So we can find a frictional value here that comes out right at 400 newtons. So I'm just going to rewrite that so we keep our 2 sigs. So there's frictional force. So now we have both of these that are acting in the horizontal direction. So all we have to do to find net force is just subtract those two. So F net is 620 minus 400, so that we get 220 newtons left over. And then that can be used to solve the acceleration, which is what this problem wants us to solve. So we're going to use F equals ma one last time. We're careful that we plug in the net force now. And so we can rearrange this. We've got 220 divided by our total mass, which was 185. And we get 1.2 meters per second squared. And then I'm going to put a positive sign on there. It's also going to accelerate, as you can tell, to the right, so you could put that as a direction also. That one's got a little bit more legwork, I think, but still pretty straightforward, as long as you remember your principles from diagram number 1, and as long as you remember how to find frictional force. So you had to do both of those things, but that's problem number 4. Let's flip over to the front. They get a little harder on the front, but still using kind of the same ideas. If we look here at number 1, you've got this guy that's sitting on tabletop. So this is diagram number 1, connected with this rope down here with object B. And object B is just kind of dangling here off the side of the table. You notice there's a pulley. They tell you a few things. It says the mass of the table and the cord are negligible, things that you don't have to take into account, so that as we're looking at this, it kind of simplifies down a little bit. Ultimately, what it wants is acceleration. So it wants to know, is this going to be enough to kind of make this thing drag along the tabletop or not? Maybe not. So if you kind of analyze it in terms of free body diagrams, you've got up here, we've definitely got friction working against this motion. And we're given a coefficient right here, so we know there's definitely friction. No friction within the pulley, but friction on the table itself. And so what we're looking at is we have to find the frictional force that's trying to stop this from moving. And if you look down here, really the force that's going to try to get this thing to move is this Fg. So it's almost a battle between these two things, a battle between the friction up top on the table and the force of gravity acting on that smaller box. As of right now, we can't say for sure if this is even going to move, because if FF's greater, then this thing's not going anywhere. But if FF is smaller than Fg, then we're going to get motion out of this. And so we'll have to kind of see what happens as we solve these things out. So let's just jump in, I think, box A, Let's go ahead and solve out things that we can start to solve out. So pretty easy to get Fg equals ma. We've got the mass. So we can solve this out. Get 49 newtons here. It's diagram number 1 because we're looking at a horizontal tabletop, so normal force is 49 newtons as well. From there, we can look to get frictional force. So we've got mu Fn, where we know both of these because we just solved Fn, and mu is given in the problem. So to get frictional force, we're just going to have to set this up. So we get a frictional force here, 7.4 newtons. So now we kind of have a value here. So now we know if Fg is anything greater than 7.4 newtons, then we're going to get some acceleration out of this. But if it's not greater than 7.4, friction wins, and this thing's going to remain at rest. So let's check on box B now. So box B, we need kind of the same information. We need to find Fg. See how much force is actually going to try to drag this system. So to do that, we're looking at using the mass of box B. So we're looking at 2.0 times 9.8. So that's going to come out as 20 newtons. If we want to keep our 2 sigs, we can rewrite like this just to stay systematic with everything. And so here's the battle. It's Fg versus Ff. So we need a net force. We're at the point now where we know Fg is going to win because we're looking at 20 newtons here versus 7.4. So this thing is definitely going to accelerate. We're going to find net force by just subtracting. So we've got our 20 minus 7.4. So we're going to get an F net. When you run this through, you're going to get 12.6. which we can round to 13 newtons if we want to keep sigs all the way through. And now that we have net force, we can plug that in to F equals ma one last time. Now what we're looking at is this is the net force acting on the whole system. And so when we go to solve the acceleration of the system, we need the mass of the system. So you got to be careful here because now we're talking about all of it together. Up here, we kept masses separate because we were just looking at the individual objects. Now we're talking about the net force acting on the system and the acceleration of the system. And so the mass of the system is the total mass that's involved here, which is pretty easy math. It's just a 5 kilogram box and a 2 kilogram box. But you got to be careful. That's an easy place to mess up. But we're going to divide this by that total. And we'll get our acceleration, and that's going to come out as 1.9 meters per second squared. It's in the downward direction here. I guess this box is moving to the downward, and then this box is moving to the right. So it's up to you what you want to come up with for a direction. I'm going to keep it positive just because this box is kind of moving to the right, but we've got multiple directions going on here. So, so a generic direction probably makes the most sense. And that's that one. It just asks for acceleration. I'll tell you, the AP folks really seem to like this setup. Seen it show up a lot more than any other force system in the past. So we'll definitely want to focus on this one. We'll run through a lab this week that kind of sets this one up as well, just to get some more practice. All right, last one, number 2 is down here is the elevator. These things sometimes get called Atwood machines as well. So if you see the terminology Atwood machine, it's just basically referring to an elevator system that's got a pulley and some kind of a counterweight that's working. So this is really the way that they set up a lot of elevators, just to lessen the amount of force that the motor has to apply. So as we read through here, we're looking at solving a couple different things. It wants the acceleration of the system, and then it also wants tension in the cable. So we actually have to do a couple of things on this one. So let's start with kind of analyzing what's going on here. You've got the elevator, we've got a mass, and then we've got counterweight, and we've got a mass. Elevator's got more mass, so we see that. And so we can kind of figure out a few different things here. I think we'll start with looking maybe at the elevator. So I'm going to come over here and just kind of label things because there's going to be a lot going on here. So let's try to keep things organized. Elevator, we have the mass. I'm going to go ahead and solve the FG of that. It's kind of a battle here if you look at it. Think about the free body diagrams. You got the FG of this versus the FG of the counterweight. So bigger one's going to win for sure. You already know what's going to happen, right? Because you've got more FG here, you have more mass. Elevator's going to go down, counterweight's going to go up, but the counterweight's going to kind of impede that motion because you've got a lot of mass to deal with here. So this thing's not just going to be like in free fall. It's going to be slowed down by the fact that the counterweight gets dragged behind. Let's just jump in. Let's solve FG of this thing, the elevator. Okay, so we get an FG here, 15,200 newtons. And then let's do the same thing for the counterweight. Let's find the FG. That's what's acting in the downward direction. Mass of 1250. Multiply this out so we can see what kind of force we're dealing with on that side. There's the two forces. So we've got 15,200 this way. We've got 12,300 this way. And so now the thing to do if we want the acceleration of the system is we need a net force that's acting on the system. So we got a little subtraction problem to do here. So I'll set that up, and we're going to get a net force of 2,900 newtons. So that's the total force acting on this system, and since it's the total force acting on the system, we can find the acceleration of the system. So that's next, which all we have to do is set this up. So we have total force on the system. We want acceleration of the system. We need to use the mass of the system. And remember, the system is two different things here. It's elevator and it's counterweight. So we have to add those two together to get a total mass if we want acceleration of the whole system. And so I'll set this up. We'll plug in. We've got 2,900 newtons for net force. That total mass, when you add those up, you'll get 2,800 kilograms. And this will come out keeping 2 sigs. You can keep 2 or 3 sigs. The original measurements have 3, but then you run into this little bit of a subtraction rule right here. So however you want to do it is fine. I'm going to call this 1.0 meters per second squared. Okay, so that's the acceleration of the system, 1 meter per second squared. So that's part one. Second part is tension. And so the key, I think, to getting the tension to work out is remembering what tension is. Tension's a force, right? And so since tension is a force, that gives us an avenue to actually be able to solve this. Because if you think, if tension is a force, then that allows us to use this equation, F equals ma. So now it's just tension force equals mass times acceleration. Now this one's a little bit different. We're going to still do net force. I'm going to label this as the elevator. Okay, so we have to kind of look at just one of these two objects. We'll probably solve it out both ways, but we have to kind of start to isolate and just look at one. I'm going to just look at the elevator, and we have to kind of think about the net forces that are acting just on the elevator itself. And so I might draw a little free body diagram over here. We've got FG, which we've been dealing with in this problem already. Tension is right here, right? Tension is in this cable. It's this guy right here. And so these two are kind of opposing each other. Not kind of, they are. You got FG going down and you've got FT going up. The problem wants this. It wants us to find FT. So that's what we're up against here. So finding this, we're going to have to kind of break down what the net force is. And so the net force acting on that elevator right here is FG and FT. You got those two things. And so the way we can set this up is we can just say the net force is going to be Fg minus Ft equals ma. And if you see why we did that, because we've got two forces acting on the elevator, Fg and Ft, they go opposite directions, so all we have to do is subtract those, and we know the mass of the elevator, and we can get the acceleration. Or sorry, we know the acceleration, we know the mass, we can get Ft, that's what we're solving for. So just checking off the list here, we know Fg of the elevator, we know the mass of the elevator, and we know the acceleration, how the elevator is going to accelerate because we solved for that here. So the whole system is going to accelerate at this rate, which means the elevator will accelerate at this rate. All right, so we're just going to kind of rearrange this. We're looking to solve for that guy right there. So we're going to have negative Ft equals ma. And we're subtracting across that Fg. starting to run out of room here. I'll try to squeeze things in. Actually, maybe I'll just transfer them straight over. So we'll take this equation, I'll plug numbers in, and we'll go from there. So we've got the mass. Now, we've been talking about just the elevator here. So it's just the tension force acting on the elevator, Fg of the elevator, mass of the elevator, acceleration of the elevator. So we've got to be careful. We're just dealing with the mass of the elevator. So this M is just the elevator, which is 1550. And acceleration of the system, 1.0. And then we're subtracting out Fg of the elevator, which we've already solved for. And we're going to get a value here of 13,600. If you notice when we rearranged here, I left that negative sign. So when you do this, you subtract, you're going to get negative 13,600. And then just remember, I'm just flipping my sign because this negative sign was in front of Ft. So this is now solved. This is Ft. Tension, the tension in that string in that rope, 13,600 newtons. Makes sense. I mean, if you look at this compared to the Fg, so here's the tension. Here's Fg. Fg wins. And so the elevator, just like we said before, moves downward. If tension force were greater than Fg, then this elevator would be moving upwards instead. But we've just kind of proven exactly what we did up here and what we talked about, that the elevator itself will definitely move downward. We could have just as easily solved for the tension using the counterweight instead. So really you can pick either one of these to work with. I'm going to show you solving it out for the counterweight just to show you that it'll work out and be the same. Make some room here. Maybe we'll do it over here on this side. So I'm just going to label that counterweight. Same kind of idea. So we're going to need a net force. Now we're just looking at the counterweight. Free body diagram is the same, right? You've got tension going up, you've got Fg going down. And if you think about this one, we know tension is greater because this counterweight's going to rise. So we know in this diagram, Ft is greater than the Fg, has to be. And so when we set this up, you can subtract it however you want, but I'm going to put Ft first, minus Fg equals Ma. So here's our setup for net force acting on counterweight. Maybe I should draw that free body diagram in. So Ft, and then we've got Fg. And then we're solving this. So I'm going to rearrange. And remember, we're just talking about the counterweight, so we just want to use counterweight numbers. So I'm going to plug everything in here. Mass of the counterweight, acceleration of the counterweight, and Fg of the counterweight. Sorry, I'm getting kind of cramped here. And if you run all of those through, you will find that that comes out to be 13,600. Beautiful. So we've just basically proven the tension in this string is the same on both sides. It's just you solve it a little bit differently if you're looking at the counterweight versus the elevator. And the only thing that really changed was I just kind of flipped these just for convenience, knowing that Ft would be greater than Fg. But if you look at these two, they're identical, which is exactly what we would think, that the tension wouldn't vary in this string. So I think that's it. Hopefully that went okay. Run those back through. I know definitely, I think in your mind, this one's probably the most difficult. There are other ways to solve this. So if you want to see those explanations, just let me know and we can work that out.